Pretty much everyone has seen an astronomical image, and they leave the most of us with a sense of awe and wonder. Can this really be what the universe looks like? Well, to answer that, no, this is not how the universe looks. These are what astronomers refer to as pretty pictures, because they are made for the public, and their primary goal is not to replicate how it looks in nature, but instead to be aesthetically pleasing. In fact, all astronomical images are actually grayscale images. We just add color to them. So let's take a look at astronomical images and their history, production, and public understanding. The telescope was the first real advancement in astronomical images. It allowed us to see details that we never could have seen with the naked eye. Using his new telescope, Galileo discovered Jupiter's 4 primary moons. Telescopes continued to get bigger and better, leading to Lord Rosse's telescope. This telescope was large enough to start showing details of distant nebulae, like the now famous M51 spiral galaxy. Telescopes continued to advance again, and eventually became our modern telescopes, like the Hubble Space Telescope. We could now capture spectacular images of outer space. A telescope works by collecting light, but light is much more than just what we see. The visible wavelengths of light are just a tiny fraction of the full spectrum. So in order to see as much as we could, we built many different kinds of telescopes that could see many different parts of the spectrum. Hubble can see wavelengths from 115 to 2,500 nanometers. This includes ultraviolet, visible, and infrared light. Hubble, like all modern telescopes, captures images using a CCD and light filters. Here is a list of all of the light filters that Hubble can use. Hubble has many different light filters, and each one lets in different kinds of light. Some filters are broad and some are narrow. CCDs capture light intensity and assigns each pixel a light intensity value. Since this is all the CCDs do, the image obviously must come out as grayscale. So the question is, how do we get from raw data like this to the pretty pictures we are so used to seeing? Rector, LeVay, Fratare, English, and Puyahu Pummel tell us that generating a color image can be distilled into the following steps. 1. Intensity scaling and projection of each dataset into grayscale images. 2. Importing these images as layers into an IP software package. 3. Intensity rescaling each layer to increase contrast. 4. Assigning a color to each layer. 5. Fine-tuning the image, which includes overall color balance, the removal of artifacts, and orientation and framing. And 6. Preparing the image for electronic distribution and print production. Here is a short video courtesy of the Space Telescope Science Institute that shows a few of these steps.
This is a Lion Prime Beats production.
Color selection can be done in several ways. The most common way is representative color. In representative color, the exposure with the lowest wavelength gets the color with the lowest wavelength, and the exposure with the highest wavelength gets the highest wavelength color. Therefore, the low wavelengths are red, the high wavelengths are blue. Public understanding of these images is not very good. Most people believe that astronomical images show the world how it would look if we could see it with our own eyes. But as I said earlier, this is not true. Smith, Arcand, Smith, Bookbinder, and Keach tell us that experts and novices look at astronomical images differently. Novices tend to look at the aesthetics first and work their way to the science, whereas experts first look for the science that the image is trying to portray, then work their way to the aesthetics. The commonality is that both groups are interested in learning just what is being presented. It is therefore important that the image creator provide a detailed description of the picture, preferably in a narrative voice. The creation of astronomical visualization metadata, or AVM, is now allowing astronomers to do just that, by letting them encode details right into the picture, so that the image description will travel with the picture wherever it may go on the internet. This will allow the public to better understand astronomical images and will help spread scientific knowledge to those interested in astronomy. I hope you have enjoyed this video, and I also hope that you have learned something in the process of watching it. My name is Evan Morehouse. Thank you.